Hello all, welcome to notes on the second lab where we measured metabolic rate. So it looks like Fraser Coast have come through with some great results here. So you can see this is the data we got from Sippy Downs and Fraser Coast have collected another data set. What they've also done is collected some additional data on some grubs, and these are rhino beetle grubs. So this is going to be great for us because this gives us a bigger size range for our insects, which was lacking before. So I've cleaned up the data. I'm going to upload this onto Blackboard. What you'll notice is we have to make sure our species are all labeled the same, because that's going to come back and be tricky later. You notice that there's a toad 1 here, and it's a capital T as opposed to a lower class T. We also have grubs here. If we want to include different individuals, we could, for example, say make a new column, and I'll call these toads. So it's the same. In that case, these could be crickets. I've given it a plural now. I should actually make these insects. So this will be allow us to differentiate between toads and insects. So I'm going to make this toads. This is all toads. Oh, there's a toad there. And this is going to be an insect. And these are all going to be insects too. So I've made a column which is going to allow me to differentiate between the toads and the insect later. So hopefully that is going to work. I'm going to save this as a CSV file. Remember, we want it as a CSV file. I'm going to put it somewhere that's easy for me to find, which is going to be my desktop for now. It's called something really complicated. I don't want to have to write that name out, so I'm going to call it Lab 2 Results 2019_3. Save that. It comes up with that. If you want to save multiple sheets, just hit OK. All right, so now we can move into R. So the first thing I have to do is set my working directory. It's random at the moment. I could go session, set work directory, and choose the directory. Or I can just try and find where my file is located. Here it is. It's on my desktop, and I can try and navigate to that desktop by just finding this pathway here. Let's do that, for example. And I'm going to copy that path, paste it into R, and then I'm going to change the direction of these slashes. So in this case, I'm going to make them all /. And now I've set my working directory. It's lab 2, what do we call the data? It's lab 2 results _2019_3, lab 2 results _2019_3. So I can read that in, and I get a file error saying cannot open this, probably because I've made some error with how it's labeled. Let's have a look. So compare lab 2 results. I forgot the plural in results. Look at that. Now it works. Okay, so now we have 34 observations, 6 variables, and remember we have this species and species 2 now, which is going to separate our insects and our toads. Temperature is not going to matter because it was all done at room temperature. We have mass, volume of CO2, and the mass specific volume of CO2. So the first thing we have to do is log transform our data, remember, because it's not going to sit onto a straight line unless we do. So I'm going to log transform all that data, and then Oh, you can see I've actually got an error here. What does it say? Error in that non-numerical argument. What is going on there? So it doesn't like this column. Doesn't like mass. What's wrong with that? You see the problem? So this needs to be a capital M here for mass. And now it works. VCO2, that works. Mass specific volume of CO2. And then I can bind them back using this C bind into that my data frame. So you can see they've all appeared in this my data frame. Okay, fantastic. We've made it this far. I can plot our data. Look at that. It's looking so good. It looks like it should sit onto a straight line. We can change the dots. Let's make them circles. Make them a little bit bigger so we can actually see the dots. And give them a color. In this case, I'm going to go pink. Oh, yes. Love it. Okay, so now I have some data points there. I can run my linear model. In this case, it's a linear model, remember, because that allows me to put this line in. But if I want to use the analysis of variance, it's the same code, but I just changed this linear model to AOV for analysis of variance, and Control Enter. And now I can see, is there a significant relationship? Yes. Look at this F value. It's huge, 133. And my P value is tiny. It's less than 0.05. These little 3 dots here. So it's very, very small. So there is a significant relationship between mass and the volume of CO2. What's the slope? Well, that's where we had to run that linear model again. If we look back into our results from the linear model, you can see here is our slope, 0.61. So that's a little bit flatter, so a little bit shallower than we normally find, but that's fine. That's still pretty close to what we expect. Remember, we're going to learn about this bit more. If it was surface area that was determining metabolic rate, we'd expect this to be 0.66. If it's absolute mass of animal, it would be closer to 1. Here we've got 0.6, so we're not really clear of what's going on there, but that looks good enough for us to continue. So what's the relationship between mass-specific metabolic rate and body mass? Let's have a look at that. Remember, this is going to be, if we plotted it, it's going to actually give us a negative relationship. So let's see if I change this to mass-specific volume of CO2. There's our negative numbers. We run the linear model, and now we have negative 0.35. So the slope's going to go down there. We can run this AB line, put a line through it so we can visualize it. And you can see now we're getting the same result where these units now for mass-specific metabolic rate are going to be in units equals mils of CO2 per gram per hour. So you can see now 1 gram of these crickets is using up a lot more energy than 1 gram of a toad. All right, so now the fun part, we want to separate out our data into toads and insects. I can do that using this line here. The toad one should work quite well. We can double check. Yes, we have 13 observations up on this side here. Now, if I run this insect one, it's not going to work. You'll see we have 0 observations. The reason that's not going to work is we actually called it insects. So I have to just make sure that I use the right name there. We run that, and now our insect data has still 0 observations. And that's because I've pointed it to the wrong column. Okay, so we need to change this to be 2 and this to be 2 because we made that second column in the data frame. So if I run that, toads now have 21 observations and insects now have 13 observations, and that should add up to 34, and it does. That's nice. So we've included all our data in that line. So if we want to make a plot, we can plot our data. It looks good there. Now we put the points over the top. So here are our toads. And they've formed those little circles because I've forgotten to change the settings for the dot. So I'm just going to copy and paste those into here. You see it's coming up with a little red squiggly line and an exclamation mark, which means I've made a mistake somewhere in the code, and it's this comma at the end. It doesn't like that. So I'm going to run that line. There's our green points. And here are our insects. So now we see something really interesting. So these are our crickets. And remember before we didn't really have a good relationship for our crickets. It was going the wrong way. When we add the grub data in, it now gives us something that's going to be a bit more sensible. And you can actually see that these grubs were a little bit bigger than the smallest cane toads we measured. So now we have a really nice data set where we can compare the slope of the line for both toads and insects. And that's going to be these lines down here. Let's see what happens if we compare the slope for toads. I'm going to run this with a green line. There's our slope for the toads. And you can see our slope, it's actually quite steep. 0.78. That's really close to the 0.75 that we expected before. So that is looking fantastic. If we run the insect data, let's see what we get. We get 0.52. So the insect data is really quite shallow, and that's probably what's making the entire slope, remember a bit earlier when we looked at the slope, making it a bit shallower. So there's our two slopes. What can we say about them? Well, we can say the slope for the toads is much steeper and the slope for the insects is a lot shallower. But the intercept for the insects is a lot higher and the intercept for the toads is lower, which means that if we're below this little intersection point, then the insects are actually we predict maybe a higher metabolic rate than the toads. But we can't really say much from this data set right now. We can definitely compare those two slopes though. So the toads look like they've got a steeper slope and the insects a slightly shallower slope. That's a really neat little summary there. Don't forget to put some labels on your axes too, using this y lab function. And so we can say, what's our y label here going to be? It's going to be the volume of CO2 in mils. I'll put that mils of CO2 per hour in this case. Because this is, remember, not mass-specific metabolic rate, this is just metabolic rate. And so there's my label here. The X label is going to be X lab equals body mass in grams. And so that looks nice now. And we could give it a main, which is going to be metabolic rates. And we get a little title for the top of our plot there. We've got to add our points back in now with which we can run these lines here, just the points line. There's our green ones. There's our orange ones. We can run these lines, put the fits in. It looks good. And we have a nice little plot that we can add in. We might add a legend, and if you're filling out for it, you can look up legend in R online and quickly find out a way to put the legend onto this plot too. Excellent. So that's a good intro on how we can run through the data and plot that out and answer some of these questions and get some of these slopes back from the analysis.